All right. So this next question asks about assessing the cardinalities of sets without necessarily having to provide a formal proof. So all of these are things that can be proved, but it's usually easier to see them via intuition. So the first thing asks about finite bit strings of fixed length n. And intuitively, it should be clear here this is finite, because you can enumerate all the strings in order of length, or like all bit strings in order of length, and eventually you'll get to very long bit strings that are longer than n, at which point you can stop, and this will have another finite time. Another good intuition for why this holds is that any bit string represents an integer. For example, 1, 0 represents 2 in our decimal system. So every bit string, every bit string represents a natural number. I should be precise. So yeah, every bit string represents a natural number. And so if you're asking for finite bit strings of length n, then you say, well, the largest number you can represent with a length n bit string is like still finite. And so you care about, and so you're asking, this is essentially asking for how many natural numbers are there up to a certain maximum. And the answer to that is because you have that upper bound, it'll always be finite. So those are both valid ways of seeing it, just by sort of imagining counting the bit strings or by picturing them as representations of the natural numbers. Finite bit strings of length 1 to n. One way to see how this follows from the previous question is that the number of these things is just going to be the sum from I is equal to 1 to n. The number of finite bit strings of size I. Yeah, because all bit strings of length 1, all of length 2, and so on and so on. And we saw above that, like, all finite. And because n here is finite, we are taking so this is not like an infinite ever-growing sum. It's a finite sum up to a certain limit, or like up to a certain stopping point. And therefore, this must be finite. And up here, I will also add that, as we saw, this must be finite. So part C is a much more abstract question, where it asks for all finite bit strings of unbounded length. So a bit string must have finite length, but it could have arbitrarily long length. And so initially, this is a little bit hard to think about, where like it's probably infinite, but we're not sure if it's countable or uncountable. And the cleanest way to see this is by realizing that, oh, it's just the natural numbers. Because if you have an arbitrary bit string of the form 1010, blah, 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 you can translate that into a natural number. And yeah, we've all basically, by doing binary counting, you know that each bit string represents a natural number. And each bit string represents a unique natural number. So if you have two bit strings that are like distinct and that they differ in their strings, they're never going to represent the same natural number. And you also know that like every natural number can be translated into a bit string. So we have one fact. And these are sort of like elementary facts about like the way the binary system works. It's just a way to represent numbers. But if you put them together, we have a bijection. Yeah. So they must have the same cardinality as the natural numbers, and so they must be countably infinite. Yeah. And the crucial fact here is that they're all bit strings of finite length, and because we know that any individual natural number is finite, even if there are infinitely many of them, so every natural number has a finite length bit string representation, and that is why we can ensure that like this function is both surjective and injective, because since every natural number has a finite length bit string, the function has to be surjective because every finite length bit string covers a natural number. The next question sort of plays with that idea a bit more, and it asks for all infinite bit strings. And the answer to this turns out to be that it is uncountable. And the reason for this is because pi is real numbers can be written as infinite strings. For instance, pi can be written as like 3.14, and is a string of like infinite length. So it's like an infinite string of like base 10 digits. And if you translate pi into binary, or any other like infinite real number with like infinite decimal representation into binary, you will get an infinite bit string. And so it turns out that with finite bit strings you could represent precisely the natural numbers. With infinite bit strings you can represent precisely all of the real numbers. So bijection between the space of real numbers and infinite bit strings. Yeah, you can also prove this by diagonalization directly, but realizing that this is just another way to represent real numbers is a more insightful way to see why this is true. Party is just out for all finite and infinite bit strings, and immediately we can say, well, it includes all of the infinite bit strings, so it is at least uncountable, so it is necessarily uncountable. Yeah.